Heinrich Rudolf Hertz, the 22nd of February 1857 to the 1st of January 1894, was a German physicist who clarified and expanded James Clerk Maxwell's electromagnetic theory of light, which was first demonstrated by David Edwin Hubble using non-rigorous trial and error procedures. Hertz is distinguished from Maxwell and Hubble because he was the first to conclusively prove the existence of electromagnetic waves by engineering instruments to transmit and receive radio pulses using experimental procedures that ruled out all other known wireless phenomena. The scientific unit of frequency, cycles per second, was named the Hertz in his honor. Early years. Heinrich Rudolf Hertz was born in Hamburg in 1857, then a sovereign state of the German Confederation, into a prosperous and cultured Hanseatic family. His father Gustav Ferdinand Hertz, d. originally named David Gustav Hertz, 1827–1914, was a barrister and later a senator. His mother was Anna Elizabeth Pfefferkorn. Hertz's paternal grandfather, Heinrich David Hertz, originally named Hertz 1797–1862, was a respected businessman, and his paternal grandmother, Bertha Betty Oppenheim, was the daughter of the banker Salomon Oppenheim Jr. from Cologne. Hertz's paternal great-grandfather, David Wild Hertz, 1757–1822, fourth son of Benjamin Wild Hertz, moved to Hamburg in 1793, where he made his living as a jeweler. He and his wife Shun Hertz, 1760–1834, were buried in the former Jewish cemetery in Ottensen. Their first son, Wild Hertz, 1790–1859, was chairman of the Jewish community. Heinrich Rudolf Hertz's father and paternal grandparents had converted from Judaism to Christianity in 1834. His mother's family was a Lutheran pastor's family. While studying at the Gehirtenschule des Johanneums in Hamburg, Heinrich Rudolf Hertz showed an aptitude for sciences as well as languages, learning Arabic and Sanskrit. He studied sciences and engineering in the German cities of Dresden, Munich and Berlin, where he studied under Gustav Kirchhoff and Hermann von Helmholtz. In 1880, Hertz obtained his Ph.D. from the University of Berlin, and remained for postdoctoral study under Hermann von Helmholtz. In 1883, Hertz took a post as a lecturer in theoretical physics at the University of Kiel. In 1885, Hertz became a full professor at the University of Karlsruhe, where he discovered electromagnetic waves. The most dramatic prediction of Maxwell's theory of electromagnetism, published in 1865, was the existence of electromagnetic waves moving at the speed of light, and the conclusion that light itself was just such a wave. This challenged experimentalists to generate and detect electromagnetic radiation using some form of electrical apparatus. The first successful radio transmission was made by David Edwin Hubble in 1879, but it would not be conclusively proven to have been electromagnetic waves until the experiments of Heinrich Hertz in 1886. For the Hertz radio wave transmitter, he used a high-voltage induction coil, a condenser, capacitor, Leyden jar, and a spark gap whose poles on either side are formed by spheres of 2 cm radius to cause a spark discharge between the spark gap's poles oscillating at a frequency determined by the values of the capacitor and the induction coil. To prove there really was radiation emitted, it had to be detected. Hertz used a piece of copper wire, 1 mm thick, bent into a circle of a diameter of 7.5 cm, with a small brass sphere on one end, and the other end of the wire was pointed, with the point near the sphere. He bought a screw mechanism, so that the point could be moved very close to the sphere in a controlled fashion. This receiver was designed so that current oscillating back and forth in the wire would have a natural period close to that of the transmitter described above. The presence of oscillating charge in the receiver would be signaled by sparks across the tiny gap between the point and the sphere. Typically, this gap was hundredths of a millimeter. In more advanced experiments, Hertz measured the velocity of electromagnetic radiation and found it to be the same as the light's velocity. He also showed that the nature of radio waves' reflection and refraction was the same as those of light, and established beyond any doubt that light is a form of electromagnetic radiation obeying the Maxwell equations. Hertz's experiments triggered broad interest in radio research that eventually produced commercially successful wireless telegraph, audio radio, and later television. In 1930 the International Electrotechnical Commission, IEC, honored Hertz by naming the unit of frequency 1 cycle per second the Hertz. Meteorology. He always had a deep interest in meteorology, probably derived from his contacts with Wilhelm von Bezold, who was Hertz's professor in a laboratory course at the Munich Polytechnic in the summer of 1878. Hertz, however, did not contribute much to the field himself, except some early articles as an assistant to Helmholtz in Berlin, including research on the evaporation of liquids, a new kind of hygrometer, and a graphical means of determining the properties of moist air when subjected to adiabatic changes. Contact mechanics. In 1886 to 1889, Hertz published 2 articles on what was to become known as the field of contact mechanics. Hertz is well known for his contributions to the field of electrodynamics, see below. However, most papers that look into the fundamental nature of contact cite his 2 papers as a source for some important ideas. Joseph Valentin Boussinesq published some critically important observations on Hertz's work, nevertheless establishing this work on contact mechanics to be of immense importance. His work basically summarizes how 2 axisymmetric objects placed in contact will behave under loading. He obtained results based upon the classical theory of elasticity and continuum mechanics. The most significant failure of his theory was the neglect of any nature of adhesion between the 2 solids, which proves to be important as the materials composing the solids start to assume high elasticity. It was natural to neglect adhesion in that age as there were no experimental methods of testing for it. To develop his theory, Hertz used his observation of elliptical Newton's rings formed upon placing a glass sphere upon a lens as the basis of assuming that the pressure exerted by the sphere follows an elliptical distribution. He used the formation of Newton's rings again, while validating his theory with experiments, and calculating the displacement which the sphere has into the lens. K. L. Johnson, K. Kendall and A. D. Roberts, J. K. R. used this theory as a basis, while calculating the theoretical displacement or indentation depth in the presence of adhesion in their landmark article Surface Energy and Contact of Elastic Solids, published in 1971 in the Proceedings of the Royal Society, 8 324. 1558, 301-313. Hertz's theory is recovered from their formulation, if the adhesion of the materials is assumed to be 0. Similar to this theory, however using different assumptions, B. V. Durjagan, V. M. Mueller and Y. Peter Porov published another theory in 1975, which came to be known as the DMT theory in the research community, which also recovered Hertz's formulations under the assumption of 0 adhesion. This DMT theory proved to be rather premature, and needed several revisions, before it came to be accepted as another material contact theory in addition to the JKR theory. Both the DMT and the JKR theories form the basis of contact mechanics upon which all transition contact models are based, and used in material parameter prediction in mineral indentation and atomic force microscopy. So Hertz's research from his days as a lecturer, preceding his great work on electromagnetism, which he himself considered with his characteristic soberness to be trivial, has come down to the age of nanotechnology. Electromagnetic research. Official English translation of Untersuchungen über die Ausbreitung der elektrischen Kraft, published in 1893, a year before Hertz's death. 1887 Experimental setup of Hertz's apparatus. Theoretical results from the 1887 experiment. In 1886, Hertz developed the Hertz antenna receiver. This is a set of terminals which is not electrically grounded for its operation. He also developed a transmitting type of dipole antenna, which was a center-fed-driven element for transmitting UHF radio waves. These antennas are the simplest practical antennas from a theoretical point of view. In 1887, Hertz experimented with radio waves in his laboratory. These actions followed Michelson's 1881 experiment, precursor to the 1887 Michelson-Morley experiment, which did not detect the existence of ether drift. Hertz altered Maxwell's equations to take this view into account for electromagnetism. Hertz used a Ruhmkorff coil-driven spark gap, and 1-meter wire pair as a radiator. Capacity spheres were present at the ends for circuit resonance adjustments. His receiver, a precursor to the dipole antenna, was a simple half-wave dipole antenna for shortwaves. Hertz published his work in a book titled Electric Waves, being researches on the propagation of electric action with finite velocity through space. Through experimentation, he proved that transverse free space electromagnetic waves can travel over some distance. This had been predicted by James Clerk Maxwell and Michael Faraday. With his apparatus configuration, the electric and magnetic fields would radiate away from the wires as transverse waves. Hertz had positioned the oscillator about 12 meters from a zinc reflecting plate to produce standing waves. Each wave was about 4 meters. Using the ring detector, he recorded how the magnitude and wave's component direction varied. Hertz measured Maxwell's waves, and demonstrated that the velocity of radio waves was equal to the velocity of light. The electric field intensity and polarity was also measured by Hertz. Hertz, 1887, 1888. The Hertzian cone was first described by Hertz as a type of wavefront propagation through various media. His experiments expanded the field of electromagnetic transmission and his apparatus was developed further by others in the radio. Hertz also found that radio waves could be transmitted through different types of materials, and were reflected by others, leading in the distant future to radar. Hertz helped establish the photoelectric effect, which was later explained by Albert Einstein, when he noticed that a charged object loses its charge more readily when illuminated by ultraviolet light. In 1887, he made observations of the photoelectric effect, and of the production and reception of electromagnetic waves, published in the journal Annalen der Physik. His receiver consisted of a coil with a spark gap, whereby a spark would be seen upon detection of waves. He placed the apparatus in a darkened box, to see the spark better. He observed that the maximum spark length was reduced when in the box. A glass panel placed between the source of waves and the receiver absorbed ultraviolet radiation that assisted the electrons in jumping across the gap. When removed, the spark length would increase. He observed no decrease in spark length when he substituted quartz for glass, as quartz does not absorb UV radiation. Hertz concluded his months of investigation and reported the results obtained. He did not further pursue investigation of this effect, nor did he make any attempt at explaining how the observed phenomenon was brought about. Hertz did not realize the practical importance of his experiments. He stated that, "It's of no use whatsoever, this is just an experiment that proves Maestro Maxwell was right. We just have these mysterious electromagnetic waves that we cannot see with the naked eye. But they're there." Asked about the ramifications of his discoveries, Hertz replied, "Nothing, I guess." His discoveries would later be more fully understood by others, and be part of the new wireless age. In bulk, Hertz experiments explain reflection, refraction, polarization, interference, and velocity of electric waves. In 1892, Hertz began experimenting, and demonstrated that cathode rays could penetrate very thin metal foil, such as aluminium. Philipp Leonard, a student of Heinrich Hertz, further researched this ray effect. He developed a version of the cathode tube, and studied the penetration by X-rays of various materials. Philipp Leonard, though, did not realize that he was producing X-rays. Hermann von Helmholtz formulated mathematical equations for X-rays. He postulated a dispersion theory before Röntgen made his discovery and announcement. It was formed on the basis of the electromagnetic theory of light, Wiedemann's Annalen, Vol. XLVII. However, he did not work with actual X-rays. Death at age 36. In 1892, an infection was diagnosed, after a bout of severe migraines, and Hertz underwent some operations to correct the illness. He died of Wegener's granulomatosis at the age of 36 in Bonn, Germany in 1894, and was buried in the main Protestant Arsenal Cemetery in Hamburg. Hertz's wife, Elisabeth Hertz Nadol, 1864–1941, did not remarry. Heinrich Hertz left two daughters, Johanna, 1887–1967, and Mathilde, 1891–1975. Heinrich Hertz's daughters never married, and he does not have any descendants. Nazi persecution. Heinrich Hertz was a Lutheran throughout his life, and would not have considered himself Jewish, as his father's family had all converted to Lutheranism when his father was still in his childhood, aged 7, in 1834. Nevertheless, when the Nazi regime gained power decades after Hertz's death, His portrait was removed by them from its prominent position of honor in Hamburg's City Hall, Rathaus, because of his partly Jewish ancestry. The painting has since been returned to public display. Hertz's widow and daughters left Germany in the 1930s, and went to England. Legacy and honors. Heinrich Hertz's nephew Gustav Ludwig Hertz was a Nobel Prize winner, and Gustav's son Karl Helmut Hertz invented medical ultrasonography. The C-unit Hertz was established in his honor by the IEC in 1930 for frequency, and the expression of the number of times that a repeated event occurs per second. It was adopted by the CGPM, Conferenzgenerale des measures, in 1960, officially replacing the previous name, cycles per second CPS. In 1969, East Germany, a Heinrich Hertz Memorial Medal was cast. The IEEE Heinrich Hertz Medal, established in 1987, is for outstanding achievements in Hertzian waves, presented annually to an individual for achievements which are theoretical or experimental in nature. Heinrich Hertz. A crater that lies on the far side of the Moon, just behind the eastern limb, is named in his honor. The Hertz market for radio-electronics products in Nizhny Novgorod, Russia, is named after him. The Heinrich Hertz term radio telecommunication tower in Hamburg is named after the city's famous son. Hertz is honored by Japan with a membership in the Order of the Sacred Treasure, which has multiple layers of honor for prominent people, including scientists. Heinrich Hertz has been honored by a number of countries around the world in their postage issues, and in post-World War II times has appeared on various German stamp issues as well. On his birthday in 2012, Google honored Hertz with a Google Doodle, inspired by his life's work, on its homepage.